Okay, cool. So yeah, so let's get back to MDPs. So that's where what we were doing yesterday. So just a quick recap is, we saw the notion of what MDPs were, like when there was uncertainty in the actions, like you take an action and where you go to is uncertain, and you had rewards. And we also saw contrast with Markov chains. And the Markov assumption comes from the same phenomenon that arises in Markov chains, where you don't care about the history, but there are some differences, mainly of having actions and rewards. So that was the main difference from Markov chains. And so we saw this notion of, it's a time evolving process, and you have rewards at every time step based on what action you took and where you landed. And so we had this concept of discounts, where the rewards that you get later on for in the later time steps matter less than the immediate rewards. And then we saw this notion of how the environment comes in between, right? To change which state you end up being in. So this is kind of like the multi-agent, the chance agent which comes in, and it's in fact the same thing. But here the difference is, like, you have this concept of policies. That's where we went to after that. And a policy, what we saw was, for each state it's a mapping, right? For each state, what is the action you should take. So that's what a policy gives you. And then we went on to try and define formally this notion of the value associated with policies. So here I said, this quantity V pi of S. So pi is a policy, and V pi of S gives the value of the policy for that state. Okay. So what it means is that at every point in the process, at every stage, what you're going to do is, whichever state you're in, you're going to take the action that pi gives you. So pi of S is the action that you're going to take. And then you will land up in some state S dash, depending on what the environment does. And this is how the process goes on. So one thing to remember is this value is a function of the policy you take as well as a state. So either you could you could interpret V pi as the value of the policy for a state, or you could also think of it as, the value of a state under a policy. So value of state S under policy pi. So this is also another way to think of it. Okay, so the important thing is that it depends on two things. So one is the policy itself and the state. Okay, so the values associated with these two quantities, pi and S. Okay, and then we try to write down formally what these expressions evaluate to. Okay, so the idea is that you start from a state S and you follow whatever pi tells you. And in the next state, again, there is a value associated, and this process goes on. So it's actually an infinite, it's an infinite depth. Okay, let's say infinite depth tree in some sense. Okay, so that's why what you do is you start from S, you take pi S, and there's a intermediate state which we call as a Q state, where you get some value, and that is based on what goes on in the next sequence of moves. Okay, so the next state, if you land up in S dash, the value there is going to be V pi of S dash. Okay, so that is in the next state what you're going to get, and there is also a reward associated with this move. So this reward is R S pi of S, because that's the action you took, and S dash. Okay, so this is the immediate reward you get, and later on what reward you get is going to be V pi of S dash. So what you write, in terms of the value V pi of S, so in terms of this state, the value you get is just an expectation over where all you can be. So it's the sum over all S dash. So this is actually a probability. So recall that this is the conditional probability of being at S dash, given you started at S and you took the action pi of S. Okay, so this is the probability, and the value you get from doing this action is the sum. Okay, Okay, so it's the immediate reward plus gamma times the reward after one time step. Okay, so again you see like it's a recursion because there's a v pi of this is actually, I mean, we wrote this as q s of pi s just to mark it separately, but what we get is v pi of s is exactly the sum of v pi of s is the expectation. Okay, I hope this step was clear. Were there any confusions on this, on how we got this expression? Yeah, I just want to get a sense if this was clear to all of you. Maybe Noel, is it clear?
Yes, ma'am.
Yes, it is clear. Okay. All right. So, what we'll do today is we'll just take an example of how you can compute this. So I'll just make use of the same example that we had on the robotic car. Okay, so this is something I had asked you guys to try out, where there are these three states, and you have the actions fast and slow, and the rewards for each of these actions. Basically rewards for each of these transitions is what you have, and the policy we have is, so let me call this pi1. So this is a policy which I'm defining as in the state cool, you're going to take the action slow, and in the state warm, also you're going to take the action slow. So this is a policy that I give you. And of course, in the overheat state, there is no valid action possible. So this is actually just the empty, it's an empty action set. Okay, there's no action that you can take here. So given this is your policy, what is the value? Okay, what's the value of the policy? What's the value of each of these states? Okay, so recall that the value function, it depends on the policy as well as the state, right? So suppose if I call it, let me say v pi 1. Okay, so this is composed of three numbers, right? So you have let me call it v1, v2, and v3, or let me just say vc, because for each state, right? So vc, that is value of the cool state. Then you have value of the warm state, and there is a value of the overheat state. So there are these three numbers which v pi 1 will have. Okay, so your objective is now to compute each of these values. So did someone try to write this down? Anybody made an attempt at it? Yes, no? So Sahil, did you get a chance to try? I'm not going to penalize you if you didn't try, so just speak, okay? Okay, am I audible?
Yes, ma'am, you are audible.
Okay, so did you get a chance to try this out? Anybody got a chance to try? Sahil, Raghavendra, any of you?
No, ma'am, I
Didn't get a
didn't
chance.
try. Like, I got pretty confused, so I didn't try.
Okay, fine. No worries. So hopefully just ask, okay, if something is not clear. So we will do this, we'll run through this example here. So what you need to do is, okay, so let's consider the cool state. Okay, so in cool state, under policy pi 1, suppose you're going to get a value Vc. So how do you compute Vc, right? So from cool, the suggested action is to take the slow action. So zoom into this part of the graph, okay, so where you have only the cool state. So basically this part, okay. So in the cool state, what happens? If you take an action slow, there's only one possibility. So you take an action slow with probability 1. With probability 1, you'll get back to the cool state. If you take an action slow, with probability 1, you'll get back to cool state. So there's no other, possibilities. Okay. So here, so let's just write it. So Vc is just going to be, so summation over all possible states you can get to. Okay. So here, so this is, let me just write it anyway. So probability of starting with cool. Okay. And the action suggested is slow. So I'm just writing it as probability of cool, slow, or let me just call it the transition function, not the probability, right? And one possibility is you land in C. Okay, so this is the destination. Okay, times some number which characterizes the value of doing this transition. Now let's just write it anyway. So the other possibility is you can uh, if it was possible to get to warm state, this transition probability times the reward, the first step reward of going to warm, plus the value of the warm state. And if this the other state was the overheat state, so the transition probability of getting to the overheat state times some reward. Okay, so remember this was actually the probability of going to C, so the destination state C given C and slow, and this was the probability of going to warm state given you started off in the cool state and you took an action slow. Okay, so here these numbers are just going to vanish because this probability is zero as per the model defined, right? Because the probability that you reach cool when you take an action slow is one, and so no other states can be reached. So this term goes off, and this also goes off. This is also zero because you can't reach the overheat state if you take an action slow. Okay, so the only thing that remains is this one term. So this value is 1. Okay, and so what do we have here, right? So remember, we are starting off with cool. We are taking an action slow because that's what pi is telling you. And now actually you would have reached a Q state, but now you're sure that you're going to get back to the cool state. That's what has happened. Okay, so now, so this is with probability 1 that this cool, that you got back to cool. Okay, so this transition had a reward of, so the reward of cool, slow, and going to cool. So what was that value? 1, right? So the immediate reward you got was a 1. Now, in the next step, you are back to cool state. So, what is the value you will get from the cool state?
Plus gamma times VC.
Exactly. So gamma times VC. So where gamma is the discount because it's one time step ahead. Okay. So this is how you would compute VC, right? And okay. So let's just write this. So you might think, okay, right, that this is one time step later. So why should these two be the same, right? Shouldn't these two be different? So yeah, if you think of it as an evolving process, this is what is going to happen, that it could be different if you started off with wrong values, but ultimately it's going to converge somewhere. So what we are seeing is when the process converges, what is the value? Okay, so and we will elaborate a little more after in some time. Okay, so I hope this step was clear, how you computed the value of the cool state, right? Okay, a show of hands or something like. Can you tell me whether it's clear? You can type, or if you want me to repeat it, you can let me know. That's fine. Yes. All right, good. Okay, so I guess a good number of you are clear. So now, so this is one set of.
Ma'am, what will be the Q state here?
So the Q state is exactly what happens in the intermediate, right? So this is Q of being at starting from cool, taking an action slow, right? So this is going to be exactly this number itself. Right, so there were different possibilities, like either you go to cool or warm or overheat, but those like warm and overheat were also not allowed here because the probability was 1, right? And so it's exactly the same number. Whatever you're computing here on the right hand side, that is going to be exactly the Q value also. right? So remember, like the evolution process was like this, right? So V pi s is exactly what you get in the Q state. And in the Q state, you have an expected value, an expectation computation, right? Depending on you have taken the action pi s and where all can you be. So an expectation over all those states. So in that sense, the V pi and Qs of pi s, that is going to give you exactly the same value. Right? Is this clear, Himanshu?
Yes, ma'am.
Right. Okay, so I'm just writing it together now instead of writing the Q separately and V equal to Q. Instead of writing that separately, I'm just combining it. Okay. Yeah. So Q C slow is exactly this same value. It's just 1 plus gamma VC. Okay, so this will give you one equation. So VC, so you can, gamma is usually known. Gamma is a parameter that you will set. Okay, so this will give you VC times 1 minus gamma is 1. So that gives VC equals 1 by 1 minus gamma. Okay, so this is one quantity that you have. Okay, so it's not always that you will get a closed form solution right away. So you will get a system of equations. So now let's just write what you'll get for the warm state. Okay, so let's write VW. Right, so what are the possibilities here? So we are evaluating the policy pi 1. So the action you have to take here is slow. Now, if you take the action slow, there are two possibilities, right? So you have this one and this is another possibility. So you can either get to the cool state or you can stay in warm, and each of this has a probability of 0.5. Okay, so let's just write the expressions once. So here you'll have the probability of starting with warm, taking an action slow. So this is actually pi 1 of warm state. Okay, and then you can get to the cool state and there's some reward, plus the probability of starting with warm, taking an action slow and hitting warm state, and then there is some reward here, plus the transition probability of going slow from the warm state and hitting an overheat state. Okay. Now, as per the transition function that you have drawn here, if you take the action slow, you can never reach the overheat state. So this probability is 0. So this is a probability, right? So this is 0. So this doesn't count. So only these two you need to take care of. So can you tell me what these numbers are?
2 plus gamma VW.
Ma'am, why are not
Plus-
considering like what happens if we take like a fast action?
So here, the policy that I've given you is if you, this is given to you. Okay, suppose I follow this policy. What is the value of each of the states?
Yeah, got
Okay.
it, ma'am.
Yeah. All right. So so can you tell me this number here? So if you
3.
so the first one is 3. That is the immediate reward. Is that right? So this one,
Yes.
right? Yeah. So this is 3 and plus what?
Gamma VC.
Plus gamma VC, because you will land up in VC. Yes. Now what about this one? If you go to the warm state,
2 plus
2.
gamma
2
VW.
plus gamma VW.
2 plus gamma VW. And this transition probability is what?
0.5.
0.5. Okay. So what you're going to get is VW is 0.5 times 3 plus gamma VC plus 0.5 times 2 plus gamma VW. Okay, so can somebody simplify this and tell me one, compressed equation? So maybe we can expand this further, right? What's this going to be? So 1.5, right?
0.5 plus gamma by 2 into VC plus VW.
VC plus 4 by 2 minus gamma.
Can you say that again? So, okay, VW equal to what?
Vc plus 4 by 2 minus gamma.
By 2 minus gamma. Okay, so this you got by expanding these equations, right? So, yeah. Okay, so do you want me to, simplify this expression? Is this clear to all of you how this came? Yes, no, I want some responses, please.
I think the equation is wrong.
Oh, it's wrong. Okay, fine. Then let's do the expansion again. So let's just write it. So you get what? 1.5 plus 0.5 gamma VC, right? Plus this gives a 1. So here you're going to get a 2.5 plus 0.5 gamma VW. Okay. So what will this give?
Multiply by 2 throughout.
Multiply by 2 throughout. So you get 2 VW. So let me just write this. So VW times 2 minus gamma, right?
Is equal to
Equals
5 plus gamma times Vc.
5 plus gamma times Vc. Okay, so let's just write this as one equation. So VW times 2 minus gamma Vc equal to 5. Okay, so this is one equation. And then we had this other equation. Vc is 1 by 1 minus gamma. So let's just keep this here for now. Okay, so anyway, you can solve these two equations to get the values of Vc and Vw. Of course, gamma will be a fixed quantity. Now there's also, V overheat, right? So this is a terminal state. So if you're going to start in the overheat position and run this process, you will not get any rewards. Okay, so we will just take V overheat as 0. Okay, because there's nothing more that happens. It's like the end state. Okay, so maybe let's just plug in some numbers to see what it gives. Let's take, suppose gamma is 0.5. Okay, so if you substitute, what do you get for these VC and VW? So gamma equals 0.5. That will give VC is what? So VC is 1 by 1 minus gamma, right? 2, right? So 1 by 1 minus 0.5. So 1 by 0.5, that's 2. And what will VW be? So this is
4.
yeah, this, right? So you'll get 4. Yeah, so gamma is half. So half times 2. So what happened? So 2 times half. So that is 1. So 6 by 2 minus 0.5, right? So 6 by 1.5, that's 4. Yes. So this is the values you get. So VC is 2, VW is 4, and V overheat is 0. So this is how you will compute this. Is this clear? Is this computation clear now to all of you?
Ma'am, I have a question.
Yes, Advait.
For the overheat state, can't we think of it like if we take any action, we end up in overheat state and calculate the value for the overheat like that?
So if you are in, say that again, like
If we are in overheat state, like we don't have a transition to any other state, like
yes.
So can we say that with a probability of 1, if we
You will
take
get back
small-
to overheat. Exactly. That is also one way to look at it. So let's do it in that way. So what Advait is telling is you have the rest of the transition diagram like what we told, what was discussed earlier. So you have all these transitions as what was drawn earlier. Additionally, in the overheat state, if you take fast, you get back here with probability 1. If you take an action slow, you get back here with a probability of 1. And the rewards here are maybe 0 itself, okay, because there's no further rewards. So if you do this, so you'll write the same set of equations starting from the overheat state. So now this would be, so value of overheat is, so if you take the action slow, for instance, okay, so whatever action, so pi is going to maybe give you some value there. So the new policy, so this will be like pi tilde, is same as pi, but only additionally with overheat, maybe one of these. Suppose you fix slow as the action, right? So then what is going to happen is, so with probability 1, you'll come back to the overheat state. And so 1 times there is a 0 reward plus a gamma times V0, right? So this would exactly be the same thing. V0 times 1 minus gamma is a value 0, right? So this will give you V0 is 0. So it's the same thing comes out here. But one thing is, since it's a terminal state, in terms of the problem, in terms of the domain, we have not defined any actions for the original problem. So it's just convenient to take V overheat as 0. But even if it helps to interpret things in a different way, this is also fine. There's nothing wrong with this interpretation. So even if you take the action as, instead of slow, if you take it as fast, the same thing is going to happen. Okay, so nothing changes here. But yeah, so I hope this is clear. Advait, is your question answered? Yeah. Okay, so is this computation clear? I want to hear from more people. Yes, Tanuja says yes. Yes. Okay. Okay. So what about the other girls? Maybe Sejal, Twisha, you guys are here? Yeah. Okay. Okay, good. Fine. So so this is for one policy, right? And we got these. So this is the policy pi1, and these were the values. Let's just do one more policy so that, I'm really sure that you all understand. So now let's just take another policy. So pi2, I'm going to consider, where I'm always going to take the action fast. So in the cool state, I'm going to go fast. In the warm state also, I'm going to go fast. And overheat, anyway, it's a terminal state, so there is no action here. Okay. So now here, I'm going to get a different set of, these vectors. So VC, VW, and V overheat. So that's going to be 3 other numbers. So again, we will say V overheat is 0 because that's a terminal state and there's nothing more you can do. All you need to do is find VC and VW. So now can you tell me what these expressions will be? So can you tell me VC? So now you're going to go fast. Okay. So maybe it helps to just copy this down there. Okay, so yeah. So can you tell me what VC will give you?
Equation or simplified equation?
Tell me the equation so that we can just go over it once. VC equals 0.5 times.
3 plus.
So which one are you telling? Of going to warm,
to
right? Yeah. So cool to warm. We are doing now. So 0.5 times 3
plus gamma
Three.
VW.
gamma VW. Yes.
Plus
0.5.
Yes. 0.5 times
5 plus gamma BC.
5 plus gamma VC. Okay. So this step is going to warm state, going to warm, and this is the going to cool state. Okay. So what does it boil down to? So you have 1.5 and a 0.25, right?
8 plus gamma VW by 2 minus gamma.
2 minus gamma VC, 8 plus gamma VW.
Can you say the whole expression? So VC equal to?
8 plus gamma VW by
8. Okay.
2 minus gamma.
2 minus gamma. Okay. So this is correct. I'm taking it by faith that you've done it properly. Right? Okay. Fine. So, okay. So this is one equation, right? You have VC and VW are like the unknowns, and gamma is a parameter. Now, what about for VW? Let's write VW. So VW, so the action you're going to take is fast. And so here there are two possibilities. Either you stay in warm or you go to overheat. So can you tell me what happens if you stay in warm?
Uh,
Those numbers.
yes, 0.4 into
0.4 times. So
4
that's this
plus
probability. This probability is 0.4.
transition
Yes.
probability.
Yes. 4
4
plus.
plus
So
gamma
yeah,
times VW.
VW. So 4 is the reward of this one step, and after this you stay in the warm state. So there's a discount gamma times VW. Okay. Now for going to overheat, what is the terms?
0.6
0.6.
into minus 10 plus 0
Yeah. So this is a minus 10
plus gamma.
plus gamma V overheat. So that is anyway 0. So it's just this much. Okay. So what will this be? So there's a large negative reward here, you see. So this is minus 6, right? Minus 6 plus 1.6 plus 0.4 gamma VW, right? Right. So what would this be? Did anybody simplify this further? This is just minus 4.4, right? Plus 0.4 VW. Okay, so here, so you see there are two equations here and two unknowns. And so if what happens if you take again gamma equals 0.5? Can somebody simplify this? Two simultaneous equations. So let's just write it. So if gamma is 0.5, so the first equation will be VC times 1.5 equals 8 plus VW by 2, right? And so this will be like 3 VC is 16 plus VW. And the second equation is this. What happened in, okay, so, okay, you can get VW directly from this equation, right? So VW times, so from the second equation, what are you going to get? VW times 1 minus 0.4 gamma is minus 4.4. So what will this give you? Did anybody finish this?
Minus
Minus
5.5.
5.5.
Minus 5.5. Okay. Yeah, and VC is what?
3.5, I guess.
So VC is
Let me check.
It's 3.5.
so this is minus 3.5,
Positive 3.5.
Positive, ma'am.
positive 3.5. Okay, is this right? I mean, I think I had some other value when I computed. So just give me a second. Huh? So this value, let's just check this once. So VW is minus 4.4. So VW is minus 4.4 by 1 minus half of 0.4. So it's 0.2, right? So, okay, what am I doing? Did I make a mistake here?
6, right, ma'am? It will be 22 by 44
So
by
0.8. Okay. So this is correct. No, it's by 4.4 by 0.8, right?
Yes, ma'am.
Okay. Okay, fine. So yeah, anyway, so you get these values. So I think maybe I made a mistake. So I got some value like BW is minus 22 and BC is minus 2. So probably that's wrong. I tried to quickly do something. Okay, so so here you see that, you know, if you take one policy, like this policy pi2 is giving you some set of numbers, minus 5.5 and 3.5. Whereas if when you took policy pi1, the numbers we got were what? VC was what? What did we get there? 2 and 4, right? So VC was 2 and VW was 4. Okay. Okay, this is even better if this is right. So if you see, if you compare these two policies, right? So now there are these two numbers. Of course, V overheat is 0 for both. Okay. Now, in terms of the cool state, this one is better. This policy is better. Now, in terms of the warm state, pi1 is a better policy, right? So, you know, so this can happen. Sometimes pi1 is a better policy for some states, and pi2 is a better policy in terms of some other states. Okay. So, what is a best policy? Is there something like a best policy, right? What policy should you really take? Okay. So, yeah, I mean, so the way I had computed, I think there was a mistake. So, you know, the way I was getting it was pi2 was better than pi1 in terms of both the states, but I guess that's wrong. Yeah, so, you know, not all policies, not all pairs of policies can actually be compared. But it turns out that, you know, there is something like a best policy. Okay, so there is going to be a policy which is better than all other policies in terms of every state. Okay, though, you know, you may have like pi1, pi2, and so on up to, you know, some n policies. These all may not be comparable among each other, but it turns out that there is a best policy pi star, which for each of the value, so the value vector of pi star will be better than every other policy. So V pi star, so pi star is the best. So V pi star of S is going to be better than, you know, at least as good as V pi of S for every pi and for every state, for every other policy. Okay. So now our interest is to compute this pi star. What is the best policy, or what's the value of the best policy? Okay, so that is what we are going to focus on next. So is this clear so far? Is whatever computations we have done so far clear?
So pi star is the policy that gives us the maximum reward, right? Or
Yes, exactly. So that's that's what we are going into next. So so the next topic is the optimal policy. Okay, so how do you compute what is an optimal policy and how do you compute it? Okay, so for this we'll have exactly the similar set of equations as before, but what we'll define is something called V star. Okay, so earlier we had a V pi for a fixed policy. Now what we're going to say is there is a V star of S, which is the value. So the best value you could get, if you start from S and are always optimal, and maybe always always take the optimal action. So there is a, you know, some things we have not very precisely stated it, but this will get clear as we go along. So what this means is that you're going to start at S. There are many actions possible, and out of this one action, at least one action is better off than everything else. So suppose you take that action. Now you will come to the intermediate Q state. And here there are different possibilities, and maybe you come to S dash. Okay, so this is still a random part. One of these will happen. Now in S dash, again, you're going to take the best action you're going to take. Okay, so I'll call this A dash. And then you will reach another intermediate state, and this will go on. So at every stage, you are going to follow the best action. If you do that, what is the value of the state S? Okay. So let's just say, let's just call it like this. Okay, maybe if that confuses. So the value, if you start from S and always take the optimal action at every stage. Okay, so this is V star of S at every state. Okay, and similarly, you can have a Q star of SA. Okay, so that is, so remember Q star is, you've started from S, you've taken the action A and you've come here. Okay, so now going forward, there is no control at this point on this action because that is the environment is doing something. It's a random action. But assuming that at S dash also things are going to be done optimally. So what's the value? So value of the Q state, SA, if in future everything, if in future all actions are optimal. Okay, so this is like a very good scenario. Like at every point of the process, you're doing something optimal. Okay, so that's what you want to get to. So let's see how to compute this. So, so again, let's write what V star of S is going to be. So you have seen what to do for a fixed policy. Now, what is going to happen is, if you took the action A, you're going to land in one Q state. If you took another action, say A2, you're going to land in another state. So what you need is the max of all these actions. And you want the next thing to be optimal as well. So Q star of SA. Okay. So Q star is going to be some value and you want the best possible out of all these, best possible actions out of all these. Okay. And so now again, what is Q star of SA? Right. So in Q star, remember this is a random node. I mean, random state. I mean, not random state. It's a state in which, the next possible state is going to be a random outcome, right? So this is going to be an expectation over all possible states, S dash, right? And it's going to be the reward that you got from that single action. So this is going to be reward SA, S dash, plus now what is the reward you're going to get if you are in S dash in the next time step. So there's going to be a V star now. So V star of S dash, because from S dash again, you're going to do something optimally. And there's a gamma times this. Okay. So this is exactly the same, the term here is just, the summation over all possible transitions you could take with this action, where all could you go, times the reward SA S dash plus gamma times V star S dash. Okay, so this is the optimal set of equations, and these are called. So this has a name for it. These set of these are also recursions, and these are the famous Bellman equations. Okay, so Bellman equations for optimality. Okay, are there any questions here? We'll just halt for a minute. Okay, you're all quiet again. Is this not clear? Is something confusing you? It's clear. No questions? Okay. Yeah. So what is the difference between these set of equations and what we did earlier when we had V pi and V star? What is the difference? Let me ask somebody, maybe Deep Gupta.
Yes, ma'am.
Yeah, what's the difference between V star and V pi?
V pi is that we calculate from the probability. V star will be the exact estimate and the best we'll get for this problem.
And V pi is what?
V pi is the estimate that we calculate in all the taking the probabilities and everything. All
Okay,
the
so yeah, so that's not fully right. So V pi is that you're given a fixed policy. You're told what actions to take, and you're going to follow that. That is what is V pi, right? And V star is if you're following the best action, the optimal at each stage. If you're going to do, that is what is V star. Okay, so V pi is not an estimate for V star. Okay, pi can be a for any arbitrary policy, but V star is an optimal. It corresponds to an optimal policy. Okay, and so you're always going to take an optimal action. Okay, so that there's a difference between these two. So V pi is not an estimate for V star. Okay.
okay, ma'am.
Okay. Yeah, it's good you mentioned it. So there may be others also who had this confusion. What about others? Can I just ask if it's clear? Jaishika, is this clear? What the difference between these two set of equations? Yes. Okay. Okay. So yeah. So what I mean. So this actually does this remind you of something you've seen in your algorithms class or anything? These Bellman equations. Does it remind you of any set of algorithms? Something you've seen anywhere else?
Ma'am, is it similar to Bellman fold?
Bellman Ford. Okay. So Bellman Ford is like the shortest path, right?
Yes, ma'am.
Yeah. So the idea is something similar in the sense that what you have here is also a dynamic program. Okay, though it's not giving you a shortest path. Okay, so it's not exactly the same thing, but yeah, the idea is a dynamic program, and this is also an optimal substructure, right? Do you remember the optimal substructure property? Have you seen the optimal substructure? So have you learned about optimal substructure and dynamic programming? Yes, no? If you don't remember also, it's okay. Just tell me whether you know it or not.
Don't remember.
Don't remember. It's fine. Okay. So what this means is that, you're trying to solve some problem to optimality, and there are these various components that come up, right? Now, if you are trying to be optimal at this S, it must be that, even in the different parts of the tree, you should have done the best. Otherwise, the overall thing that you would have, overall action that you would have taken at S itself won't be optimal, right? If there was a something better that you would have done in an intermediate stage, then even in the optimal, when you try to construct what is optimal at each state, you should consider that you are optimal everywhere else also. So that is what is this optimal substructure property. Like in the case of shortest path, right? If you're trying to, like, an example is there's a path from S and these nodes, right? S to T, the two terminal nodes, and you're trying to find the shortest path from S to T, and maybe you go through a set of nodes. So if this is the shortest path from S to T, then the shortest path from S to this node or S to some node like this, that also, I mean, the path from S to these intermediate nodes, that also has to be the shortest possible. Okay, otherwise this overall path will not be the shortest possible itself. Okay, so that's the same idea here. So that's so this is actually a dynamic program that plays out here. Okay, so this is also, the idea here is also the same. At every stage of the tree, you have to be optimal. Only then will, at the root, you'll be optimal. Okay, the value computation will be optimal only in that case. Okay, so we are running out of time. So tomorrow, what we will do is we'll see a way how to solve this. So these are the set of recursions that you have, and it's not obvious how you will solve this. Okay, you need something more. So this is how a characterization of the optimal value function, but how do you compute this? This is so what are the algorithms that you can use to compute it? This is what is going to be the next topic. Okay, so I will stop here for today, and maybe I'll just hang back if you have some questions. So if not, thanks everyone.